Okay, now, okay.
Yeah, that's good.
And I have a little fraction. That's why
I'm glad you, did you get on the Edinburgh?
Yeah.
Did you get on the Edinburgh?
Good.
Oh, you did it from last night, yeah. With another connection. Yeah. Yeah, I've had that. And every so often it goes wrong and you have to do it all over again.
There's no.
Yes.
It's just a which parameter range you cover somewhere there.
So, are you going home after this again? We just saw yeah, he's here because he had to evacuate from Israel. He took a boat to Cyprus and then he got a flight from Cyprus to. So he came in just to say hi to him. He was just out of coffee. I was there, so yeah. But the day or more on a boat getting to Cyprus was apparently was a cruise. Yeah, everything seems very tranquil here, but there are storm clouds on the horizon that we will worry about. Okay, okay, welcome back, everyone. It is my special pleasure to introduce my colleague, Eva Andrei, who's going to tell us about her work on flat bands, topology, and quasiperiodic Moiré. She's one of the pioneers of this field, and we're really happy to have her here telling us about her research. Welcome, Eva.
Thank you, Piers, for the invitation, and it's a delight to visit London and the theater scene. So that's an opportunity to be physics and fun. So what I'm going to tell you today is I'm going to start with the first part. I'm going to talk about flat bands, why they're interesting, and why the applications in two-dimensional material are particularly experimentally accessible and interesting. And I'm going to focus on flat band superconductivity and especially on magic angle twisted bilayer graphene. And we'll talk about topology there and superconductivity. And in the second part of the talk, I'm going to talk about a double Moiré system where you have a magic angle twisted bilayer graphene that is sitting on top, aligned with a boron nitride sample, and you can change the configuration. And there are all sorts of surprising and interesting things that happen there. In particular, there are incommensurate lattices. We're going to get quasicrystals and what we call intercrystals, which I will explain later. And we're going to see how that affects the electronic property, and that is all done with scanning tunneling microscopy. So let's get started by way of motivation. Remote is not working.
You have to press there once.
Click on
Click once.
Yeah, just click on
Click
this.
once and you'll be fine.
Click on what?
Just
Click on the
Can you do that?
Yeah, just
Focuses
so
on
the
the
focus is on. Yeah.
Actually, can you remove that?
Okay,
Oh, yeah,
okay.
if you click on the
Yeah.
more three dots at the top, and then you in the floating controls.
Ooh.
Yeah, exactly, up and a little bit over. So yeah, you can't see your mark.
What do I click on now?
Yeah,
It's very difficult to do because actually you probably don't see the same picture. So this one,
Perfect.
and then if you say hide floating meeting controls, then the annoying bar disappears, and we can make you a little bit smaller there as well. Good.
We have to go back to our slides. We have to go back to our slides.
All right, just do that.
Okay, thanks, Tuna. Okay, so here are the people that did the work, the STM team. Shinwan Lai, Go Hong Lee, Angela Ko, and Indra Neil. And here are the transport people. I'm probably not going to get to transport data. That this is the heavy fermion stuff that actually Andre Bernard talked about at the beginning of the conference. So I won't have time to get into that. And here is our Japanese collaborators who are growing these incredible hexagonal boron nitride crystals, and our theory collaborators from Rutgers. So let me get started with flat band. Of course, we all have heard about flat band, and why are they interesting? Because the kinetic energy is quenched, and then correlations can pop up and give rise to all sorts of interesting correlated phases. And in particular, superconductivity is particularly interesting in flat band. So when you have standard BCS mean field theory, and you write down your gap equations, and your energy dispersion here has a gap, and the excitations, and in conventional weak coupling superconductors, where the coupling is much smaller than the bandwidth or the Hawking, then you can linearize the excitation here near the Fermi surface, and what you get pretty straightforwardly is that TC is exponentially suppressed in the coupling constant, and rho here is the density of state at the Fermi energy. And again, my pointer is not working. Okay, here it is. Okay, this is the density of state. So the only way in this case to increase superconductivity, to increase TC, is to increase the density of state. And that traditionally is done by doping. You can do chemical doping, you can do intercalation, and for example, graphite calcium doping gives you a TC about 6 Kelvin, and with electrolytic doping, you can dope TMBs using ionic liquid, and you can get up to maybe at 10 degrees or 12 degrees. So about 3 decades ago in the 90s, there was this group of Russian expatriates theories from that worked in Finland, and they came up with this very intriguing idea. And they said, okay, what if this epsilon here, this is completely zero? So basically, you have no dispersion in the excitations, you have a flat band, and that this integral becomes very simple. And lo and behold, you get the DC, rather than being exponentially suppressed in the coupling, it is linear in the coupling. And omega here is the volume of the flat band in reciprocal space. And then you see, instead of the pairing, Cooper pairing happening in a thin sliver around the Fermi energy, it actually permeates the entire Fermi sphere. And this led Volovic to speculate that, and to kind of show back of the envelope calculation, that you could get room temperature superconductivity in graphene. So this is very nice. But then somebody noticed that, okay, if this is really zero, if you have a perfectly flat band, of course, your effective mass diverges. And okay, so what good is that? Because in that case, if you look at the London equation, the superfluid stiffness here, which is a prefactor here that determines your superfluid current, is going to zero because the effective mass is infinite. And then, okay, so then the superfluid stiffness goes to zero. So even though your TC for pairing is no matter how high, you will never have anything useful because there's no supercurrent. So to the rescue came another Finnish group, Pavi Torma here, and she realized that there is a way out. So if your wave function has a non-trivial geometry here, then she calculated that there is an additional term in the superfluid business, which is a geometrical term. And she showed in 2015 that this geometrical term is proportional to the Chern number. And in that case, you have a lower bound, and you can get supercurrent. A few years later, Andre Bernavig actually showed that this is there is a much less restricted condition. It's enough to have quantum geometry. It's enough to have a Berry phase or quantum geometry in general. Yes?
So this whole argument is starting with the assumption that there is a flat band, right?
That's
So
right.
that's actually not realized.
Absolutely, absolutely. So we're gonna have to
Should we
work
make
hard to
that
get,
argument all over,
we
or
have
should we
to get-
start where we?
we have to work hard to get there, but you're right, you need a flat band, otherwise it's pointless. But not only a flat band, okay? As we see here, flat band is not enough. It has to have a non-trivial topology. So you need two things to realize Waller's string, flat band plus non-trivial topology. Okay, so most of you will tell me, okay, we've known about flat band with non-trivial topology forever. And what are those? They are Landau levels, right? So this is an example of Landau level in graphene. Here we have the two K points. They're related by time reversal symmetry. You apply magnetic field, you slice the band structure, and you get these beautiful Landau levels. They go like square root, the sequence, the energy sequence goes like square root of the Landau level index and magnetic field as opposed to linear, just because of the linear dispersion. And these are STM pictures, and this is what the density of state looks like, electron sector, hole sector. So we already have that. So what's the big deal? Well, the big deal is that we need a magnetic field. So we already have that, we have flat bands. Okay, you bring your Fermi level in between the gaps, you get an integer quantum Hall effect. That's a proof that there's topology here, there's a finite Chern number, and you bring your Fermi level into one of these lambda levels, you get the fraction of quantum Hall effect, and this is a proof of correlation, a correlated state. But the problem here is, okay, this is not very interesting because we need a magnetic field. Can we achieve all this without a magnetic field? Is that possible at all? Going back to Silke's question. So I know of three ways of doing that. One way is the well-known magic angle twisted by the graphene. It turns out that there's a sort of a resonance effect when the twist angle, you see the twist angle is the ratio of the interlayer to intralayer tunneling. And there's a special angle where you get kind of a resonance that gives you a flat band. So and this flat band can be mapped exactly onto pseudo-Landau levels, as I will show. The other case that I know about is applying a periodic strain. We've done that with graphene. This is a buckled graphene. And you can create a periodic strain lattice. And strain does give rise to pseudomagnetic field, which has pseudo-Landau levels, and we have them here, we've measured them here. It gives you a pseudomagnetic field. The strain gives you a gauge field. And if it has a special form, you can actually get a pseudomagnetic field, pseudo-Landau levels, and you can map everything. You get flat band that you can map onto Landau levels. And I'm not going to discuss this today. And the third case that I know of is line graph lattices. And then here you have bipartite lattices, and you have symmetry protected chiral flat bands. This is dice lattice, Kagom and Lie lattices. You always have a flat band due to the bipartite structure. And I'm not going to talk about that. This is a very, very interesting direction to go into. Now, yes?
So that was actually my point. So in spite of having these conceptually flat bands, which result from very simplified description of these models, the experiments that try to realize these flat bands show that these are actually not flat bands, right? That was more my point. So
Right.
yes, I know
Right.
that's
So as you see in graphene, they are not actually flat band, but if they're completely flat, you're not going to get it. You're going to get localization. So there is you won't get the topology. That's the main point. You need both flat and topology. You cannot get topology if it's completely flat. And Andrei talked about this at the beginning of this.
Perhaps a way of asking it differently is your simple theoretical models, how robust are they to perturbations around truly flat? So I assume there is some degree of robustness to semi-flat.
So it's pretty robust if you put that into the integral there,
Yeah.
and yeah, it is, you
Yeah.
can go a little bit around.
Exactly, and that sort of
Right.
helps you escape Silka's concern.
Yeah, so it's
Yeah.
not completely, yeah, so that argument still holds if it is, you want the U over T to be close to one. Not one.
Actually, yeah, maybe just a comment. I mean, there are known lattices where you can, with quite short range hopping, make the bands almost exactly flat. So there's no,
One.
I mean, even beyond, yeah, the magic angle ones, but okay, there's some residual dispersion, right?
Right.
Then, given that, you can ask, well, what terms would you have to add to the Hamiltonian to make it perfectly flat? And it turns out that these are very realistic terms in some circumstances.
But then you lose the topology, I think.
No,
No, you don't.
without disturbing the
Yes,
topology.
see, actually.
So
these
there are
ones are
lattice models
topological also, yes,
of
that's-
lambda levels, basically, so you can get bands that are exactly degenerate like a lambda level, yet only have hopping terms on a lattice to maybe second or third nearest neighbor to very, very good precision.
I would like to hear about this.
Yeah,
Okay,
I'll show you.
Okay. Okay. So, okay, why 2D and why we have 2D is because we have extra knobs where you can tune things. So for example, you can have a substrate that you can modulate with the potential, you can twist it, you can apply strain, and that controls the band structure. You can gate electrostatically and that controls the Fermi level with a gate voltage. You can change the distance of the screening plane so you can kind of control the interactions. So there's lots of knobs and that's why we like 2 dimensions. But there is a catch here. Okay, there are lots of knobs, but the downside is just because it's 2D and it's so easy to control, it's extremely sensitive to external perturbation. This is a really, so unless you get really rid of external random potential or substrate-induced potential that you don't want, you're not going to see anything. You're just going to see your substrate. So that is a huge consideration and it's a huge problem for 2D material. Okay, so like to give you an example, in the old days, when people discovered graphene, the only way of making a sample was to deposit it on silicon dioxide, which is copied from the semiconductor industry. But then silicon dioxide is a horrible substrate. It has dangling bonds, it has charge centers, etc. And here, as many people have shown, this with many techniques, this is an example from Amir Yacobi's data with a single electron transistor, and you see you have huge modulations in the local density of state. What this means is that your Dirac cone is riding on this random potential, and when you do a macroscopic measurement, you actually average over this whole thing, so you smear out all the interesting physics that happens at low energies like this. So you round off your density of state, which should be linear, and when you do SDM, you completely lose whatever is going on at the Dirac point, and the same it happens in transport. Okay, so one has to be very careful about that. So we said, okay, what is the perfect substrate for looking at graphene? And there is no more perfect substrate than graphite. So you put your graphene on graphite and it is perfect. And then you bring your STM and look at it. Now, the way a sample like this has to be prepared, your graphene sits on top of graphite, but it cannot be, the distance has to be a little bit larger than the equilibrium distance, which is about 0.3 nanometers. So when you just put it on top, or you did the inverse exfoliation trick, you exfoliate your graphite. Instead of looking at what's on your tape, you look at what's left behind. And sometimes you have flakes that are floating on top. And that we can find with STM. We see the steps, we see those flakes. And when you do that, okay, with STM, there's 2 things that you can measure. One is taking advantage of the exponential dependence on the height. And then you raster the sample and you see where the atom sits, and you see the corners are the carbon atoms. And the other measurement that you can make is take the derivative with respect to the bias voltage, and that gives you something proportional to density of state. And you see this is beautiful. We have recovered all the physics at the Dirac point here, the Fermi level in STM is always, the origin is 0. So we see here we have a little bit of hole doping of hole doping, and we can nicely separate Dirac point physics from Fermi level physics.
Oh, sorry, it's kind of a stupid question, but what's the difference between graphene on graphite and just graphite with another layer?
Okay, so graphite with another layer, you see all the other layers. So the dispersion changes. You don't have Dirac cones, you have kind of, so you have to, if you want to see graphene, you have to suppress the tunneling into the bulk. And that you do, because it's exponentially dependent on distance, it's enough here, we were 20% above, larger than the natural separation. When you go to natural separation, I don't have the paper here, that it's very different.
Okay, thanks.
When you
Could
just
this-
go to graphite.
Could this be AA stacked? You
So
you think it's suspended, right? But could it be AA stacked?
It could be anything stacked. I'm gonna show you, yes.
The problem with this is you have no control over angle.
Absolutely.
So you're just sort of ripping the Band-Aid off and hoping
No
that something
control.
stays behind.
The control came years later.
Yeah.
Okay, so this, you apply magnetic field, and, okay, you see these beautiful lambda levels pop up, the square are dependent on B. Now you see there is a gap here at n equals 0, to your question. So we could not understand where this gap, the gap actually survives with 0 magnetic field, there's a 10 millivolt gap. So we wonder, is this an excitonic condensate, or is this because we have alignment, we're breaking the symmetry, and we couldn't tell. And the only way to tell was to get rid of the graph, to suspend the sample. Otherwise, we had no idea what this is. We were really intrigued by this gap here. Okay, so how do you suspend it? So this is what you do. You make your sample.Ese are the leads. The graphene is on top, and then you dig a trench underneath with a nasty acid, and you suspend your samples. You can make a hole bar. You can make a 2-terminal geometry. These are all sorts of other suspended samples that we made. And what we saw with the suspended sample, we saw the fractal quantum Hall effect at 1/3. So first of all, people didn't believe their correlations in graphene at all. So this actually proved that this is not a trivial uncorrelated system. There's not only that, but it is much stronger than in gallium arsenide. You see, we already see at 2 Tesla at 300 millikelvin. We don't have to go to the magnet lab to see the fractional quantum Hall effect. Very strong interactions. Okay. So, so the next thing is, so we wanted to do STM. We wanted to figure out what that gap is from. So we couldn't do it on the suspended samples because they were very small. You can't bring the STM there because it kind of collapses. So we had another idea. Let's have CVD ground graphene and put it on the TM grid. This is the grid. So the holes are about 15 microns. So we deposit this huge. When you do chemical vapor deposition, you can have very large samples. And this was grown by Jing Kong at MIT using not the standard growing it on copper, she grew it on nickel. And what we didn't know at the time, when you grow graphene on nickel, you actually grow bilayer, and they're twisted. And the twist is kind of random. So when we looked, so we will go into one of the suspended samples, you get twisted bilayer, and we had every possible angle is there, twist angle. So now we could come in with the STM and look at it, and just to show you what happens. Okay, you've seen this a million times. Okay, so this is the Moire lattice. The size is inversely proportional to the twist angle. A is the lattice constant. One interesting thing about this, to which I'm going to come back later, as an experimentalist, this is extremely robust because I don't care how the layers are aligned. If I have a shift, you see the pattern doesn't change with the shift. So I don't have to worry about that. I don't have to worry about aligning it. This is very useful, as you'll see later. Okay, so we came with the STM onto this suspended sample and 20 degrees, 3.5 degree, you see the pattern gets bigger and bigger as expected, like A over theta. We're getting up to 1.8 degrees. So, okay, this is not a big deal. People have, I mean, one of the first observations, and when STM was first built by the IBM group, this is one of the first experiments that were done with graphite, and they immediately saw Moire pattern. No big deal. We knew that they're there. This was known since the 90s.
Did you have the independent measurement on the angle or just deducing it from the?
So you look at it from the FFT and from the Moire.
Oh, okay, so you don't have any. So you're just looking.
But what came as a huge surprise was that not only does it make pretty patterns, but it also gives you reconstruct the band structure. So a large twist angle. So we get Van Hoff singularities with separation is kind of linear in the twist angle. And you see as you decrease the twist angle, they come in closer and closer. And by the time you get to what we now call magic angle, they merge and you get one flat band. At the Fermi level, you have a little gap, which coincided with the charge density wave that we saw with the in topography and in density of state maps. So now if you go, these are twist. So this is the Moire, this is the Van Hoff singular separation as a function of twist angle. And it kind of goes to zero by the time we're at 1 degree. We didn't understand this very well at the time, but we had theory help. And then we could measure the Fermi velocity using Landau level spectroscopy. And you see the Fermi velocity kind of follows, it kind of comes down as you approach this magic angle. So the electrons slow down as they're supposed to if we have a flat band. Okay, so this was back in 2009, and as somebody mentioned here, there was no control on the substrate. We couldn't control the twist angle. Suspending sample is extremely challenging. So that's when we needed technical breakthroughs to be able to control this. So the first big technical breakthrough came from the Corey Dean's group, who collaborated with Watanabe Taniguchi, found boron and put the sample on boron nitride, and then they could observe the fractional quantum Hall effect without suspending the sample. The next breakthrough, very important breakthrough, came from the Austin group, from Manuel Tutuk's group, where they figured out how to actually control the twist angle to a very, very high accuracy. And so now we have the toolbox for twistonic, and the field could explode. And many, many different kind of 2D materials could be made. The first demonstration of such a sample using these techniques was from Pablo Jaria Herrera's group. Here they had the field effect transistor, and when they cooled it down, as you all know, it went superconducting. And then there was an avalanche, which continues of results, both theoretical and experimental. And what I'm going to mainly focus on is topology and quantum anomalous Hall effect. And we'll talk a little bit more about superconductivity. So, okay, let's talk about the band structure. Okay, so we have a top layer, bottom layer, Moire pattern. And in reciprocal space, they look like this: green for the green bottom graphene, red for the top graphene. You see these two Dirac cones. Their separation is proportional to the twist angle in reciprocal space. We must remember that they have opposite chiralities because they come from the two K and K prime points that are related by time versus symmetry. And we have 8 degrees of freedom, 8 orbitals per Moire cell, 2 valley, 2 sublattice, 2 spin. Okay. Okay, so this is a calculation of the band structure, and you see when you hit 1 degree, you get a flat band that it's separated from the remote band. And you see the twist angle runs here. And at 1 degree, you get this beautiful flat band. Okay, so what are these bright spots here that we see? The bright spots correspond to AA stacking, where every atom in the top layer is a neighbor in the bottom layer. The dark spot correspond to either BA, where a B atom is sitting on top of an A atom, and the B atom in the top left is on A atom in the top left is no neighbor, and vice versa in the AB part. Okay, so when you calculate the registry index, which is the ratio between the AA regions and the AB regions, it doesn't matter what the twist angle is. It's always the same. They always have the same area. Okay, it doesn't matter what it is. But in fact, if you look at the energetics of stacking, you see that AA stacking is extremely expensive. It costs about 20 millivolt per atom to actually have an AA stacking. So then the lowest energy stacking are ABBA, we have a saddle point in between that's a little bit higher. So of course, if the system can, it will reorganize, it will adjust to minimize its energy. So when you and so it's going to pay strain energy in order to gain van der Waals energy. And you see that by the time, if you take this into account, when you go to 0.3 degrees where you have a huge Moire cell, the AA regions shrink to a tiny percent of the air. Of course, they can't go away, they're like vortices, but they shrink a lot. Experimentally, we see the same thing. This is 0.28 degrees. These are the AA region, ABBA, and these are the saddle points here. What's interesting also to see that this relaxation here involves a vortex of, I don't know if you can see these little arrows, but the atoms are shifting clockwise a little bit in the top layer and anti-clockwise in the bottom layer. So there is an actual vortex that is created of lattice displacement. So when you not relaxing the structure, there you have a flat band, but it is connected, it's not separated from the remote band. And what relaxation does for us, which is very, very important, it actually separates the flat band from the remote band. So what we have here, this flat band is an isolated flat band. It is, one can show that it can be mapped onto a 0th lambda level. It is 8-fold, and therefore it has topology. It's 8-fold degenerate. Again, the lattice variant spin. And the band filling is controlled by electrostatic gating. And this is how we count it. When you have an empty band, when you're here, your Fermi level is here, we call it -4. When you have 4 electrons, it's 0. And when you have 8 electrons in the full band, and we call it +4. And not here is 1 carrier for Moire, which is inversely proportional to the square of the twist angle. Okay, so how do we see that this looks like an n equals 0 pseudo lambda level? If we look in, let's say, one valley, we look at the K valley, and we write down the Hamiltonian. You have 2 blocks. This is the Dirac bi-Hamiltonian. Sigma is the Pauli matrix that operates on the sublattice degree of freedom. Dot P on the top layer, sigma minus theta 2 dot P in the bottom layer, and these U's are the intra-layer tunneling operators. And this is in a layer basis, okay? But if you switch bases, if you go from the layer basis to sublattice basis, this is what happens. So the top block is sublattice A, the bottom block is sublattice B. So now the Hamiltonian acquires a gauge field, which has opposite signs in the 2 sublattices, okay? So these are bonding and anti-bonding states in the A sublattice and the B sublattice. So if you take the curl of this gauge field, of course, it's going to be very not uniform, but at the center, it is maximum. And it's of the order of 100 Tesla. Okay, of course, it goes to zero away from at the edges of the Moire. And so you see immediately that this looks like a lambda, like a n equals 0 lambda level, but you have opposite fields in the two sublattices. So I can draw it like this. I'm sitting in the K valley, and you see that on the A sublattice, which are the red arrow here, the pseudomagnetic field points up, and on the B sublattice, the pseudomagnetic field points down. Okay. And if you do that in the K prime valley, it's all reversed by the time reversal symmetry. So in the K prime valley, the A sublattice pseudomagnetic field points down, and the B sublattice points up. And if you look at if you label the state, you can label the state. Now we have 4 labels actually: spin, valley, sublattice, and churn. Of course, one is redundant. So you label them like this, and whichever basis you choose depends on the experiment that you do. So you see, when you don't, these 8 levels are degenerate. So it doesn't, you throw an electron, they don't care where they go. And this degeneracy is protected by inversion times time reversal symmetry. So there's no way to lift this degeneracy and to reveal the topology without breaking one of these symmetries. So if you want to reveal this topology, you have to either break inversion or time reversal. Breaking inversion you can do by aligning it with, for example, nitride, breaking time reversal with magnetic field. Both experiments have been done. The inversion was done by these 2 groups, Andrei and Gordon. Time reversal was done by our group. Okay, so let's look at breaking inversion symmetry. So let's say that I have my graphene here. The A and B sublattices are populated by the same carbon atom. And I have boron nitride, which is a sister lattice, which looks pretty much like graphene, except that you have different atoms in the 2 sublattices, which gives rise to the large gap, to the 6 EV gap. And now if you superpose the 2, you have broken the inversion symmetry because the energetics, when you put a carbon atom of boron, it really likes to sit there. It has a lower energy than when you put it on nitrogen. And now we've broken the symmetry. So if I'm throwing in electrons, they will first go on the carbons that sit on boron in this pink region. And when I'm done with that, when I'm getting to my 5th electron, I'm going to have to put them on the other sublattice. Okay. And so if I have a partially filled band, if I have odd filling, I will. So you see the churn number here are the minus plus here. Yeah, okay. So if I have an odd filling, I'm always going, no matter what I do, I'm always going to get a finite churn number that is going to show up.
I thought they had different lattice parameters, so you're going to get some sort of moire or mismatch.
Excellent question.
Okay, great.
Excellent question. That brings me to my next topic. But this is how it was analyzed.
Yeah.
Okay. And if you analyze it this way, so these are the results from this is Andrea Young group. So what they did, so notice that let's say that I have a filling of 3, which means I threw in 7 electrons. There's 1 electron missing. Now you see that missing electron could be either in the churn number +1 or -1. It doesn't care. It has the same energy. So if you look at the sample, you won't see an almost quantum Hall effect. But if you break this symmetry by applying a magnetic field, so let's say you apply a positive field, and then it's going to like to align so that the pseudomagnetic field aligns with the external field, and now you read a churn number of +1. You just add up all these churn numbers, and this is what they did. And then you come back with the field. There's a hysteresis here. So it's 0, the magnetic field. It is still churn number of 1. You overshoot, and then it's going to sit in the other valley, and you get a churn number of -1. So that's what you're doing. Now, if you hadn't applied the magnetic field, they could be in different parts of the sample, they could be turnover +1 or -1. You wouldn't see anything. You need a magnetic field in order to see that. Okay, so now the flatband topology, room temperature superconductivity. Where is it? Okay, so indeed, superconductivity was discovered, and this is the famous phase diagram where you see a beautiful two superconducting domes that flank an insulating phase, and this people is reminiscent of the high temperature superconductors. People got very excited about it. So there's very strong coupling. TC over TF is 0.2 or so. And the more exciting thing is that instead of having every point of this phase diagram having to make a different sample, all you need to do here is change the doping. You just turn your voltage, and you can plot the entire phase diagram in a single sample. Okay. And so isolating phase flanked by superconducting domes, we have a pseudo-gap phase that we saw with STM, which happens above here. We have a nematic phase also in this regime about it, and people have seen strange metal behavior, the linear and T-resistivity. So there's many signatures that resemble high temperature superconductors.
How did you know that was pneumatic? Just out of curiosity?
Oh,
Is it static
okay,
pneumatic?
this is +1 electron per Moire. This is -1 electron per Moire. And what we did is you move your Fermi level. Okay, the way you know that, so if you just integrate over these density of state, the IDV curve. So let's say that my Fermi level is here. I integrate from here to here. I know the filling, and then I integrate from here. I know the bandwidth, so I know how much, what the filling is, and you do that at every point. And you end up with the line here being 1 electron per Moire, and this is one whole.
And where are you on the phase diagram when you sing that again?
I am
So if you
the
look at the
filling.
thing,
I'm about.
You're above, is it the white area maybe?
No. I don't have the phase diagram for this. I'm around filling 0 here, but it can also be seen at other fillings. But it was mainly seen around filling 0. So on this phase diagram, it will be somewhere here. There are other superconducting domes. So it is somewhere here.
Oh, look at that. Okay,
Yeah.
thank you.
Eva,
Yes?
can you remind us, how is the superconductivity characterized? Transport, also tunneling, how do these
This is transport.
transport?
There's also a SPM data. We will see the gap.
Thank you.
Okay, so magic angle TBG scorecard. Okay. First of all, there's only a fraction of the samples. If you know how hard you work, and every lab has a different record, like we have about 30% of the sample are superconducting. One of the big problems is twist angle inhomogeneity, and you can see that with STM and with other techniques. Another problem is, Volovich progress from temperature superconductivity. It's no matter how perfect your sample is, it's never above 4 Kelvin. So what's the problem? Why can't we get to higher TC here? So if we look,
I think one of it was probably thinking about microscopic angstrom lattice constants, not Moire lattice constants.
well, yes, microscopic. Well, no, yeah, you were thinking about graphite, yes. So yeah, this is Volovich's formula. But if you take the volume of the flat band in the Brillouin zone, it's only about 0.06% of what it would have been if this was graphite. So if we could make, now we could actually so you want to increase the twist angle to decrease the period, right? To increase the volume of the flat band of Brillouin zone. And you see the magic angle is a ratio of the intra-layer to interlayer tunneling. So one trick to get there is to actually apply pressure. And this was done by this group here at Columbia, but they apply a huge amount of pressure, and they were only able to change it from 1°.127. TC increased a little bit, but this is not the way to do it. One has to figure out another way.
Work with so many different high pressure groups. Huge amount of pressure means different things to different people.
3 gigapascal.
Oh, low pressure.
Okay,
Oh, no, talk to me
Yeah.
highly in a minute.
so
If you,
if I remember correctly, it was 3 gigapascal.
All right.
Okay,
Okay.
so maybe going higher would do it.
I don't think
I
so,
don't know.
because you have substrate and other issues,
Yeah.
but I just wanted to know what pressure you're.
Yeah,
above.
yeah. Yeah, for me, 3 gigapascal is huge, but yeah. Okay, so I think that the kicker is here, maybe we have to increase this volume of the flat band. Okay. Next,
Back to my original point,
what?
even on the perfect magic angle Quasiperiodic graphene, if you do that like band structure calculation, it's not flat. So what? I don't really get it. So it's not because it's
It's not
imperfect that
flat,
it's not
it's not
flat.
infinitely flat, but
Yeah.
this is not the kicker. The kicker is, I think, it is the volume in reciprocal space, which is much too small.
It's hard.
Maybe if it's flatter, it would be higher. I don't know.
Perhaps. But
Okay, next topic is Moire. This is Moire. Okay, so here back to your question, Paul. Okay, so this is a wonderful story, but graphene is and boron nitride don't have the same lattice constant. It's off by a couple of percent. Okay, so therefore you can never really perfectly align it except for 2 points. Okay, so there's 2 cases where you can align it, and that is you have to be, if you want to be at magic angle, the twist angle between the bottom layer and the graphene has to be 0.55 plus or minus, or 0 here, and that's it. And now here's the issue with the shift. Okay, here's my first graphene layer. I'm bringing in my second, rotate it to 1.1 degree, and this is to scale. So this is my Moire, and I hope you can see it. And I'm bringing my boron nitride, and then rotating to 0.55 degree. You see, you have a beautiful superlap. Okay. And now, as an experimentalist, I can't really align my atoms. So it can be shifted by a little bit. The problem is you shift it by 1 atomic space. The change is of the order of the Moire. There is a huge magnifying factor, right? So, hitting it exactly at those angles is practically impossible. Okay, so how did those guys do it? So what Alan McDonald and collaborators show that these are shifts on the order of the atomic scale. So when you perfectly align, you have a permeate, you have a Chern number of, let's say, +1 everywhere. But if you shift by 1 atomic spacing, you can hit at the green region, which is 0 Chern number, or the blue region, which is -1 Chern number. So you can never know where you are, and you have twist angle disorder. You'll never see it. So we were very puzzled by the results of the transport result. How on earth could they actually get that, right? Given the lattice mismatch. So that was the motivation for looking at SDN. You see what's going on with this topic. Okay, so unless you have the precision of alignment is 0.02, which is absolutely impossible. We don't know how to align 2 different materials. The technique doesn't work. So it is a big experimental challenge. So that brought us to our SDN. So here is this is a picture of the sample. So this twisted bilayer graphene on boron nitride. These are our electrodes. And then we look at the pattern that we form. Okay, so we see a perfect crystal here, a one-to-one commensurate, the two Moire lattice are one-to-one commensurate. Here it's a strain commensurate. Now here we have a Moire of Moire. And here we have a Moire, Moire, Moire. And now we have Moire quasicrystal, and I'm going to discuss all these separately. And this is a Moire intercrystal. So what is it that we're actually looking at here? What are the bright spots and what are the dark spots? So let's go and analyze this. So when you put graphene on boron nitride, carbon sitting on boron is going to look like this. You're going to get a dark region with a bright halo around. And when you put graphene on graphene, you're going to get these very bright points, bright regions, which are the AA lattice. And now you superpose the two. And for example, in this particular, when you have LGG is 3 times LGBN, you're going to get something like this. These are the AA regions, and these are the GBN region, okay? And then, okay, and this is an actual sample. So what we have to do to find the lattice constant of GG is to measure the distance between the bright regions here. And if we measure distance between the dark regions, we get the lattice constant of GBN, okay? So once we have that, we can go to reciprocal space and we find KGBN and KGG. We can immediately calculate the twist angle and we can get the strain out of it. I'm going to show you one example of how we do this. So one important point here, when you are perfectly aligned, one-to-one alignment, which is where we want to be, you don't see any dark spots. It's only the bright spots that show up. Okay, so here is in reciprocal state, this is my first, the bottom graphene layer. This is my second graphene layer, so Kg bottom, Kg top, and this is KGG not is without any strain. And now I'm bringing in the boron nitride and I'm aligning it and at 0.55 degrees, and this is what it looks like. When I zoom in here into reciprocal lattice, because the twist angle is very small, these reciprocal lattice vectors are kind of straight for the graphene, and this is the boron nitride one, and of course they're different because of the lattice spacing different. And alignment means that there's a 60-degree angle. You have a equilateral triangle here. That's what alignment means. So the K at 0 means unstrained. KGG naught is equal to KGB and in magnitude. Okay, and once you know that, you can calculate. You can calculate what the twist angle is. You can calculate theta GG, theta GBN. You can calculate the relaxed Moire rates, 12.8 nanometers for 1.1 degrees. And now if you have strain, let's give one example of strain. Let's say that the theta GG is a little less than 1, so these two graphene wave vectors are going to be closer to each other. So the system is going to relax in order to create alignment because that lowers the energy like this. So you're gonna basically graphene is going to stretch, and so these lines are going to get shorter, and you get alignment, and we can exactly calculate the final KGG and KGGF from the FF2 topography, and we can extract the two twist angles, which we don't know a priori, and we can extract the strain, and here are the formula. And I'm not going to bore you with the formula. So let me give you an example here.
So why is it that there's only one sort of mutual size of these Moire zones that makes them exact multiples of each other? It seems like you can tune them both more or less continuously. So why can't you make them different multiples of each other? So
say that again?
What's the selection criterion? I mean, you said there's a single case where there's rigid lattice alignment.
Oh,
But in principle, I mean, the Moire unit cell seems like you can tune it quite.
So I want a
quite
1.1,
continuous.
right, for theta GG to be a flat band. And then in order to align it with the GBN, there's 3 angles. There's plus 55, minus 55, and 0. But the 0 one is a higher order thing, so it's going to be much weaker.
So I mean,
zero
why is,
plus or
why are they
minus-
so rare? What is the main constraint? Is it that
It's
you need
just-
to
it's just
stay within the
It's simply that
sort
you're
of
not-
angle range that gives you still good flat bands? Or, I mean,
No.
because it seems like, well, you showed the example where the unit cell's just three times. more.
You need 1.1 degree.
You need 1.1 degree to have the
1.1
flat band.
is fixed.
That's,
Okay, you can't vary that much.
that's rigid, because we want the flat band. Yes, but you can find other ones, higher order ones. So I didn't write down, there's a formula, PQ, and there's three integers,
Okay, there
right?
should be some.
Yeah, there's a
Yeah.
formula, yeah, there's a whole series of them. But we want 1.1 and we want it to be robust, so these are the three cases. The two cases actually, the 0 is much less robust.
So I have two questions. One, you were talking about strain, if it's not quite done. Strain in which of the graphites?
Which one?
Well, you said there would be strain in the graphite sheet. In the one against the
You
HBM?
can have both. You
Okay,
can
and
have
how do you tell?
homo strain
Okay.
or hetero strain. We assume that it's mainly the top one.
And in many devices, you have HBM, graphite, HBM. Now, I hesitate to introduce yet another Matryoshka, but
That is the kicker. You're
Okay,
absolutely
fine.
right. You're absolutely right.
Okay.
Yeah. Yeah. I mean, HBN is wonderful until you have alignment and then it messes everything up. Yes, okay. Okay, here's an example. Okay, so here we have, we don't see any dark spot. This is a 1-to-1 alignment. So L Moire is LGG is equal to LGBN. Reciprocal space, you see the K vectors of the two are on top of each other. And we can calculate the twist angles. We can calculate, so they're 1.03 in this case and 0.3, okay? But there's strain and we can calculate the strain. So in this particular example, we have about 0.3% strain. And you know, every sample we can analyze and get out the numbers. Okay, so we have dozens and dozens of these patterns. So we can plot a phase diagram here of the lattice spacing, the Moire spacing of LGBN and LGG. And these lines, the solid lines are, this one is 1-to-1 alignment, 2-to-1, 3-to-1, 1-to-2. And this is the rigid lattice alignment. This is the McDonald point here, where it's perfect aligned. For 1-to-1, there's also points for 2-to-1 and 3-to-1. So now we're looking at this sample here. This one is perfectly aligned. It's 1.1 to 0.55. It sits right here. Okay. Now we have another aligned one, 1.03.3 that I showed before. It sits right here. And then we have about a dozen of other ones that sit along this line. Each one is, the only one that's unstrained is this one. Okay. And then, of course, we fill this phase diagram with sample. Okay, so let's first focus on the 1-to-1 alignment. If you look closely, you'll notice that there's nothing, we have no points within this, what we call basin of attraction. So every lattice that would have been here, presumably is going to find its lowest energy and gravitate to 1.1. We don't have a basin of attraction for any other ones. So it's only for the 1-to-1. So you can be as far as 20% from the rigid lattice alignment and still be 1-to-1 aligned. And that's why probably we think it was possible to see it with transport because there was this alignment, this relaxation effect. Okay, now let's talk about the points that are off the 1-to-1 alignment. Those are not a periodic crystal. They're quasi-periodic crystal. So let's compare periodic and quasi-periodic. So on the left, we have the 2D Bravais crystal, and they're spanned by 2 lattice vectors. We call it rank 2. Now, the other vectors, or the other ones, are spanned by 4 lattice vectors. and we call it rank 4 in this particular case. So there's no block theorem on the when you have these 4, when you have a rank larger than 2 in 2 dimensions. So you have to go to a high 4-dimensional hyperspace, calculate your band structure and project it back to 2D, or find more friendly methods to do it, numerical method to do it, because going to hyperspace and projecting is extremely challenging. And then you can look at long range order. Both have long range order, and that is manifested by the fact that you have sharp brachy. And then you can look at the allowed rotational symmetry. On the left, we have only 4, 2, 3, 4, 6. On the right, it depends. So we have the well-known quasicrystals, which have all these properties, but they have any rotational symmetries other than the Bravais, the Bravais symmetry. So experimentally, there's only one that was, they're very rare. They're in aluminum iron. So experimentally, they have a 5-fold symmetry. Do you have other symmetries?
Decagonal. 10.
You have you have
Oh, sure.
okay, we have that too, okay.
Yeah, but one question with quasicrystals. Resistance on the crystalline ones shows metallic. And for the quasi-periodic, is the temperature dependent resistance just flat? It's a question.
We didn't measure it,
Did anyone measure it?
I don't know.
That's tragic.
We only measured the density of state and band structure, but not
But,
transport.
You know, our earlier speaker has been measuring resistance on a lot of things. Do you know if there's been transport measurements in this region where they're allegedly quasi-periodic?
I think the only example I know would be the people try to do it on the graphene, right? Just the graphene. People have not
So-
attempted to do it on the
Right, because
DMD.
this would be fascinating, because you have beautiful diffraction, but one of the hallmarks of a quasicrystal is ether wire. It's just flat. It has a residual resistivity ratio.
Yes, right.
And the decagonal phase is particularly interesting because it's aperiodic in the basal plane, periodic perpendicular. So you get metallic transport along the periodic direction. And again, just horrible flat resistance. So a beautiful experimental difference between these would be the metallic you see in the 2D Bravais and just temperature
I
independent.
see, interesting.
So that would
Okay.
be a fascinating comparison between bulk quasicrystals and these.
Okay, okay,
All right,
homework.
yes?
And actually, a corollary to this, a more simple corollary was, what are you?
Moiré, simple.
Thank you. Are all these quasi-periodic states insulating, or are there some metallic, some
And
insulating?
well, you'll see, it depends where you put, where you gate it, okay?
Yeah, in
We have,
quasicrystals, they're mostly crap metals.
Yes.
There were a few that were thought to be insulating, but that did not stand,
But I'm asking about
or
hers.
hers, okay.
So
No,
it
I know
depends
about-
on where you
that's
put
the
your
reason I
permit.
asked,
Yeah.
because I know in quasi-crystals that are bulk, that's the situation, but I thought it might be quite interesting if
So,
Eva had insulating.
so we don't have transport, but we have density of state. And you'll see that, that it's interesting, yeah,
And also, of course, people who see localization.
Yeah. absolutely, yes. So these are quasi-crystals,
Sorry,
yes?
over which over
What like?
large are the quasi-crystalline regions in your sample? Are there like?
They of the order
Does
of
it
few
cover all
hundred,
the
a
entire
few hundred
sample?
nanometers,
About
a few hundred nanometers, 50 to
Okay,
two
so then I
hundred.
don't have to do the transport on that scale.
It's really hard, yeah. Yeah, but you know, one needs some more technical breakthrough to look at that. So these are the quasi-crystals, and we were trying to call ours quasi-crystals. Paul Steinhardt said, verboten. You cannot call ours quasi-crystals because quasi-crystals have these forbidden symmetry and you don't have them, which is true. We only have one. So we had to call them something else. So basically the symmetries that you can get are mostly Bravais symmetries. We get one 12-fold, one dodecahedron you're gonna see, but most of them are not. So we were not allowed to use quasicrystals, so we call them intercrystal. Okay, so they're intermediate between crystals and quasi. Okay. Okay, so we are in graphene, people have seen a quasicrystal. You have to rotate by 30 degrees, and then you get, of course, quasicrystal, but it's the only one point, right?
And the symmetry of that is 5 or 10?
It was 10
10.
here. Okay, so here is an example. Here's an intercrystal. So we have two lattice vectors, and the angle here between them is 30 degrees. So when the projection of one of the lattice vectors on the other is the irrational, that's when you can say you have quasiperiodicity. There are all sorts of caveats on that, of course, because we have a finite sample. So we calculate how far you have to go before you see something periodic. If it's like 10 times larger than your sample, you say, okay. And this is our quasicrystal. We have one. And we have 12 points here, but they're not quite quasicrystal because you see, so these are our six peaks, and in between we have, I don't know if you can see them. These are the other peaks at 30 degrees come from Moiré of Moiré. So it's a superposition of the KGBN and KGG, and then that gives you another K vector that's exactly at 30 degrees, has kind of the same length. So you get something that looks like a 12-fold symmetry, but it's not quite, okay? But that's as good as we can get without going to 30 degrees. Okay. So here we have this phase diagram now. We have the twist angle, and we have many more points by now. My postdoc calls it a box of chocolates. So yeah, commensurate, the white ones are the commensurate ones. The purple ones are the intercrystals, and the blue ones are the very rare quasicrystals with the caveat that I mentioned. Okay. So the next thing to ask is, okay, what does that do to the band structure? What does it do to the electronic properties? So here we have a sample that has a little bit of strain. It's a one-to-one align. This is a topography. It looks beautiful. The 6-fold symmetry in the Bragg peaks. And then you do the density of state mass. You take the Fourier transform, and you see that actually no matter where we go, at what energy we go, you always see the same kind of Bragg peaks. They don't change. The intensity stays kind of the same. And then when you do DIDV map, which means every line here, vertical line, every horizontal line, it's a fixed gate voltage, a fixed doping, and you vary the bias voltage, or you can go, basically, typically go horizontal line. And you see, this is our flat band, which is roughly the same flat band as you see without the boron nitride. And you see that as the Fermi level goes through this band here, you open gaps, and we could see that more clearly here. So these this should be correlated gaps. We don't know what they are at this point. And it kind of looks very much like what you see in TBG that is not aligned to boron nitride. The big difference is that it is very far from the remote band. The remote band in TBG is at kind of 20, 40 millivolts away, and the remote band here is very far away. So the alignment has done something to the band structure. Now let's go to an intercrystal. So this one is 1.98 degrees and 1.02 degrees. And now what you see is every energy, the Bragg peaks are different. So they light up and they get darker. And I'm going to show you a movie. So these are our 4 lattice vectors. And this is now the density of state map. And you see it's very different from the one where it was one-to-one aligned. Extremely, completely different. It's unrecognizable, but we still open a gap at the Fermi level. And here it's actually an even larger gap. And then finally, we go to the quasi-crystal, again, the same thing. Which Bragg peaks light up depends on the energy. So, and here you see the dodecagonal symmetry here, the 12 peaks. And you see again that they come from a linear superposition from the KGG and KGBN. And now the band structure looks even more different. And here I'm comparing it to the perfectly aligned one. So very, very different behavior with just tiny changes in the twist. So let me show you the movie now. So we have, okay, so I'm looking at this point here. And look at so the outer are the KGBN and the inner one are the KGG. And you see how some of them light up as a function of energy. And that has to do surely with you create localized states at different energy, and you get extinctions from the form factors go to zero for some particular energies. And that is because of the quasi-periodicity, where basically this is like a scattering problem, and there's some energy where you can go through and others you cannot. And how am I doing time-wise?
Got about 15 minutes.
Okay, so I can get to this last part here. Okay, so so the question is, so let's say that in the transport measurements, they did have aligned regions as we have seen are quite prominent, and they're quite easy to get to. So what were the edge states that they were looking at that gave rise to the anomalous Monty Hall effect? So, so here is a simple model that by our theory collaborators. So this is a Frenkel-Kontarova model. So they model the AA side by masses and the elastic energy in between them by springs, and they put it in a periodic potential, and with the height U naught is basically the van der Waals energy in a Moiré, and then they can just minimize the energy. You can calculate the elastic energy, which comes from how far you are from equilibrium position, and you calculate the potential energy here, and then you minimize the energy, and then you see what happens. So obviously, when you're perfectly aligned, there's no problem. You're going to get these huge domains. So if you are in the rigid alignment condition where these springs length is exactly equal to the distance between the minima, you're going to have absolutely no problem aligning your entire sample. But what happens when you're a little bit off, when you're just a little bit away from the rigid lattice alignment condition? And here is an example. So rigid lattice alignment, you see these nice Fourier peaks, the Bragg peaks. This is the aligned lattice. Now you're 5% away, and now you see, so the color scheme here tells us how is the distance, how far you are from the equilibrium distance. So basically, the redder you are, the more strain you build up at the edges. So you see now when you are 10% away from rigid lattice condition, you're going to create aligned domains that are broken up by boundaries at which the strain, so you think of it, as you keep stretching and stretching, and eventually it doesn't take to stretch anymore, you break, and then you have to start all over again. So these are these boundaries here. So no alignment in these boundaries. You're missing a line of Moire, and now you are 10% away. Now here you're 10, here you're 20% away. So the domains keep shrinking, and as you go further and further, they become smaller and smaller. So that's the point. So you can get alignment, but you cannot get global alignment. you're gonna break up your sample into regions that are aligned, separated by regions that are aligned in a different way. And they're separated by these boundaries. So let's look at such a boundary. So yes, and strain increases upon approaching a domain. Okay, so this is an example. Here we have a commensurate lattice. And just to make this clearer, you see that we have a tensile boundary here and we have a shear boundary here. It kind of zigzags. It likes to go along crystallographic axis. If you zoom in here, the tensile boundary, see that the moires are kind of stretched and you leave an empty spot in between. This is you have a missing line here in a sense. A shear boundary on the two sides of the boundary, the moires are displaced in opposite direction, and the tensile domain walls are just about one Moire lattice wide. The shear ones are much, much broader. So, so now we're going to look at the density of state map. And so we're looking in this region here we're at filling of 3. That's where the anomalous quantum Hall effect was observed. And the bias voltage is 20 millivolts, and we do a map here. And you see that in the commensurate region, it's completely dark, it is gas. And we have a one-dimensional edge state here, conducting state. Now, just a very important point here, this state here is one line below the boundary of the sample. So just at the edge of the sample, at the boundary, we don't have anything. So now, if I'm looking at the IDV spectra as a function of position, I'm going along this line, I'm here, so you see nothing, I'm in the gap, and now I'm hitting the edge state, I'm getting a large density of state here and now. So are these the chiral edge states that we are all after and that give rise to the anomalous quantum Hall effect? And then we kind of repeated the experiments that the transport people have done. So we're looking at this corner here, and I'm marking the AA regions. And now I'm applying a magnetic field. I'm going to a finite field here, and then I'm coming back. So I'm going to fit 500 millitesla, and then I'm coming back to 0. And I'm doing the density of state map. And so what I've done here, I mapped the AA region to the topography figure, and they're here. But I see the maximum of the density of state is shifted by a little bit. And it's sitting, actually, instead of being at the AA, it's shifted to the AB. And that is kind of, if you shift, there's the correlation between the sublattices and the K valley. So it looks like we're sitting in one valley, and then we're going in the opposite direction of the field, half a Tesla, and then back to 0. The same excursion that the transport people did. And again, we put our AA points here. And now we see that the maxima have flipped. So there was a shift. And now it looks like they have shifted to the K prime value. So it looks like what we have here is we do have a finite Chern number here. And it depends, just as in the transport measurement, it depends on how you break that symmetry. So then we were wondering about, okay, is this edge state, is it a chiral edge state? Can we say something? So what we did, we look at the Fourier transform, we take it very close to the edge state, and you see that there is a broken symmetry here. So the plane waves that go normal to the edge state is the 1, and the one that goes in this direction is 2, and the one that goes in the opposite direction is 3. And you see that when you're going with a positive magnetic field, 2 is less than 1 and 3 is less than 2, so you're kind of going clockwise. And when you're going with the opposite magnetic field, 2 is it's going in the opposite direction. Okay, they're going counterclockwise, so it's tall, medium, short, anti-clockwise. So it is possible, this is not a definite proof, we need that, we are trying to figure out other ways of doing it, but it is suggestive that these edge states here are the ones that could be responsible for the observation of the quantum anomalous Hall effect in transport. And
So-
if the sample is sufficiently small, if your sample is really smaller than one of these aligned regions, then you should be able to see these edge states. Now, I must mention that this perfect quantization that was seen by Andrea Young's group was observed in only one sample. Nobody ever reproduced it, including Andrea Young. So it's very, very fragile, and you really have to hit it right, or else you're gonna see something less. Gordon probably had a few domains in there, so it was not perfectly quantified.
So those are the Fourier transform of the entire image.
No, it's only very close to the edge,
Oh, yeah.
So we're zooming in.
Zooming in Fourier transform the edge, and those are the big Brillouin zone. The peaks or the moire. It's just
This is the Moire.
the moire part.
Yeah.
But the previous, you're talking
It
about the
was-
real
no, it
atom.
was Only Moire, no, we only talk about Moire here. So the Moires here are our atoms.
Sorry, maybe I missed something. I thought normally for the anomalous Hall, you have some sort of moment or very curvature or something. But do you have that here? You're turning on a.
Oh, yes, well, there's a turn, this is a
Okay,
turn
so
of one.
Oh, I see.
Okay, turn of
I
one,
missed
and
that.
then you go, okay, so the important thing
Yeah.
is that at the edge here, we have a missing line, which means that it's like a vacuum.
Oh, I
Right,
see.
so here's a real edge, so in that
Oh, I
sense,
see. Okay.
if you should have an edge
You have
state
very
right
curvature,
there.
'cause you have
Right,
very
you do have very
That's,
curvature.
I missed that. I couldn't understand how you.
I mean, you can't have a churn number without there, so.
Of course, no, but I missed why you had an anomalous Hall.
So, but you have to break all the symmetry, otherwise they're kind of
Yeah,
on top
okay.
of each other.
So
That's
But
a
then,
good
I
point.
but then I guess I didn't quite understand, why do you have to turn on a field then?
Because otherwise, there's gonna be some region of the sample gonna be +1, okay, so this is
Oh,
the,
so you have domains between.
you'd have domains,
That's-
because they have the same energy. You need to lift that degeneracy, and
Alright.
then it kind of, you pin, your energy to a particular
Oh, I understand.
region, and then come back to the magnetic field, but it's still stuck in that state with turn 1 or -1. So you need a magnetic field, otherwise you can't tell.
And if you switch the magnetic field,
So that's, okay, so that's what we did here.
Yeah.
Right, you go to one direction. Okay, so you measure, this was the transport measurement. Okay, and then, but we are going in this direction, measure and come back to 0, measure the spectra, and then go in that direction, come back to 0, measure the spectra. This is rho IX, this is what the transport people do.
all right, thank you.
So we're doing basically the same experiment, only measuring something else.
can you image the atoms so that it's seeing
Uh,
really it's this
yeah,
polarized
yeah.
or that polarized?
Yes, we can, and it's on our list of things to do. Yes, it's much easier to.
Because you
the
directly
Moire.
see whether it's this churn band polarization.
Absolutely, yes, it's on a to-do list, yeah, thanks. Okay, so this is a summary, and, okay, and, thank you for your attention.
Time for questions? Or lunch? There have been a lot of questions already.
Yeah, you said that the not inconsistency in these samples about whether or not they are superconducting. In samples that do superconduct, how consistent are phase diagrams between samples?
In some that you do see superconducting what?
In the ones that you do see superconductivity, how consistent are the phase diagrams?
How consistent they are?
Yeah.
In terms of it, what field, they're very consistent with what everybody else is doing. And now we are mainly now looking at tri-layer graphene, but yes, so you get superconductivity around filling 2. Yes.
The question, yeah, sure.
I think I'm trying to understand that the you try to do a Fourier transform only on the edge part. But why
Like
not
a
the,
few lines below the
Uh-huh.
edge part.
but why not the bulk? The bulk is also chiral. right?
We've also done the bulk, yeah.
And that you also see the same pattern in the bulk.
So we haven't done the whole, we do have for the whole bulk, and does show the same thing, yes.
Okay,
But we wanted to kind of focus on the 1D channel. And we really kind of don't understand exactly how it works. I'm like, okay, I think that, so if you think of momentum and energy conservation, you're sending in a beam of electrons. And then because there is this edge states that allows only momentum in one direction to get to transport, depending on which direction you go, you're going to deplete one set of waves and not the other, and depending on which. But we really don't. We would like to understand this much better. I mean, it's kind of a hand waving argument.
yeah, and
We really don't very well
but because
understand
and
it.
also you have different bulk domains, and when they meet on the edge, do you have a counter propagating or
So no, it depends if
both are
I
like a-
would have, if I don't apply the magnetic field, I have both. But if I apply the magnetic field, then it's spin to one K vector. Yes,
So these domains are quite big, I guess. So-
this
so
one,
is
it depends how far you are from
But
really
what-
large,
only-
600 nanometers, this one.
So one question would be, could you bring multiple tips to such a domain wall and actually measure transport through?
Multiple tips.
Yes.
Yes, wouldn't it be nice to have multiple tips? $4 million.
Well,
It's very hard to have multiple.
Trump doesn't help.
I mean, it's like it's two STMs basically.
Right, but I mean, is
But
that
in
just
principle,
science fiction or
yes.
is that something you could do?
No, there are people who there's groups that have 4 tips. So in principle, yes, but we only have one. Yes. So what ideally what you want to do is this, and we are thinking of how to do this. Okay, so you bring your tip, you can touch and shoot an electron and have a detector out here, and then
Right.
either it's depending on how you change the field, it's either gonna get there or not. So we're thinking of how to do that. It's quite challenging, but because I mean, a priori, we don't know where to put the leads, and yeah.
Right, sure. You have to image first,
Right,
pick
right.
your spots and then do the experiment.
Or 2 tips, yes. 2 tips will do it.
John, the question.
You mentioned the early Volovik papers. I seem to remember, wasn't that about black bands in rhombohedral?
So
Right, if
so
you're
they
working on that, could you?
he had flat bands in rhombohedral, he had flat bands in just graphite, and then he had this spiral defects, right? So so basically it was all based on TBG twist, having a twist between the layers.
Can you engineer rhombohedral?
So no, and rhombohedral people have done, and one can do that, and it is superconducting, but TC is low. So TC is low, and what is omega there? I don't know actually. TC is low, even though omega is pretty large, because it's just the unit cell is small.
That's what.
So maybe that has to do with how flat it is. Yes.
Other questions before we break for lunch? Well, let's thank Eva for a great talk.
Wait. First, we've just absolutely failed to get a conference photo all week, so let's try and get one now. Okay, you get one. So just everyone to the front. Get a photo. And then you can tell us. Yeah.
If you come back.
Well, we can try again.
actually even you have polarized everything to one domain, you can still get a counter propagating.
Yeah,
because
I mean.
one goes
everyone in
straight
the
the
park,
top,
that's-
but the other will still
We'll get
go
some
this
groups
And the